Hi students, today we are going to discuss a new topic, the projectile motion. As you can see in the video, all the parts of those angry birds are projectile motion. Basically, it's a non-linear motion. In the last topic, we have covered linear motion. So now we are going to discuss non-linear or curved path. Basically, it's a two-dimensional motion where the object moves in two different planes. So let's discuss a very simple type of projectile motion, that is something thrown perfectly horizontal. Means the initial velocity is perfectly in the horizontal direction. Now let's see what are the directions, important properties of projectile motion. One of the important thing about projectile motion, you are familiar with these quantities, the SWOT equations you have seen in the last topic. Only force we are going to use the same equation here also. As a result, for that, let's see what are the directions. Acceleration, initial velocity 9.8. You are throwing the object at any moment if you consider the path. So that's the direction combination of initial velocity two motions. Now a vertical and a horizontal any velocity after initial, for our convenience we are splitting vertical and horizontal the final velocity. This and is a final velocity, all the calculations another final velocity to use, and when it hits the ground it's a final velocity because it's an accelerated so any velocity motion after initial can be considered as a final velocity. Now let's see the other quantities, the acceleration. As you know, always the earth is pulling downwards, means the resultant force on the body is always vertically downwards. As a result, the acceleration of the body is always vertically downwards. Coming to the displacement, there are two types of displacement for a body under projectile motion. A vertical displacement, you can see it's coming down some distance in the vertical direction. At the same time, it's moving horizontally also. So there is a horizontal displacement as well. Now, if you observe the directions of this quantity, what you can see, all these vectors have different directions. What's the problem in having different directions? You cannot directly add or subtract these vectors. The initial velocity is perfectly horizontal, but the final velocity is at an angle. And there's a vertical displacement and a horizontal displacement, and acceleration is perfectly downwards. This is the problem with projectile motion. In the linear motion topic, all the quantities were in the same line. So it was very easy to use the equations of motion. But here, everything has different directions. So what are we going to do? Before going to the equations of motion, let's see how these quantities are going to change during the motion. So let's think about the acceleration. What happens to the acceleration during the motion of the projectile? As you can see, nothing will happen to the acceleration as Earth is always pulling the ball downwards. Always the acceleration will be acting vertically downwards. Now, the velocity. You can see initially you are throwing perfectly horizontal. Means the actual velocity of the body at the beginning is horizontal. So the red colored arrow I am using for the actual velocity, and the violet color is for the horizontal part of it. Initially it's just horizontal, but once it leaves your hand, you can see another velocity is increasing downwards. That's the vertical velocity, because the earth is always pulling it downwards. So once again, let's see what happens to each velocities. There is a horizontal velocity and there's a vertical velocity, and there's the actual, the resultant velocity. So clearly observe what happens to each velocity. The violet colored horizontal velocity, nothing happens. Why there's no change in the violet colored component? Because in order to change the velocity, you need a force. There is no force acting in that direction. In the horizontal direction, there's no force. A very important point in projectile motion, there is no force acting horizontally, but there is a force acting vertically, which is the weight of the body. And as a result, you can see what happens to the resultant velocity. The resultant velocity is increasing because one component is increasing. So this is how the velocities change during the motion of a projectile. The horizontal velocity, no change. The vertical velocity increases and the actual or the resultant velocity increases. Now displacement. You can see as the body moves forward, there are two types of displacement. It's coming downwards as well as it's moving horizontally. So both vertical and horizontal displacements are increasing throughout the motion. The horizontal displacement is generally called the range of the projectile, and the vertical displacement, as you know, it's the height of the projectile. Let's conclude the properties of this type of projectile motion. What we have seen is there is a horizontal as well as a vertical motion. The properties of horizontal and vertical motions are completely different, or they are completely independent of each other. The basic difference is there is no force horizontally, but there is a big force vertically. That makes all the other differences, like there is no horizontal acceleration. You have seen the velocity is same throughout because there's no force, there's no acceleration in horizontal direction. But vertically, the situation is different. There is a weight acting. As a result, there will be a downward acceleration, which is the acceleration due to gravity. Now, the horizontal velocity, as you have seen, remains constant, but vertical velocity increases. Generally, it changes, but in this particular example, it's go on increasing. Now let's see how to solve the calculations in projectile motion. We have to use the equations of motion for calculations. We have discussed in detail in the previous topic what are so what equations and how we are going to use them, and the directions of each quantity we have seen. Now what's the problem with vectors? Let's see this equation. You want to find the final velocity of a projectile, and I'm using the equation v is equal to u plus at. But remember, v, u, a are vectors. Do you remember what was the direction of final velocity in that diagram? On hitting the ground, this was the direction of final velocity. If you want to use this equation, initial velocity should be like that. Acceleration should be like that. But we know they are not in those directions. Initial velocity is perfectly horizontal and acceleration is perfectly vertical. This is the problem in using the equations of motion directly in a projectile motion. The directions of each quantities are different. Sometimes they are exactly perpendicular. So how are we going to add or subtract them if they are not in the same line? The solution is we are going to split everything either horizontal direction or vertical direction. So let's see how to use the equations in horizontal and vertical directions. For example, if you want to write an equation horizontally, like v equal to u plus at, you have to make sure all the quantities are horizontal. Or you have to take the component of all the quantities in the horizontal direction. Everything should be horizontal, whether it's a component or the actual quantity should be horizontal. Same way you can even write in vertical direction, but everything should be vertical. Ut plus half at square, but make sure u, a, s are horizontal. In this case, if you write in vertical direction, make sure u, s, a are vertical. Even the other equation, every equation you can write either vertically or horizontally. There's no combining of horizontal and vertical quantities. But if you observe, this is horizontal acceleration. Already we have discussed previously what is the horizontal acceleration. There is no force in the horizontal direction, so the horizontal acceleration is 0. What is the result? The whole term got cancelled. Because it's 0, the entire term is going 0. That will happen even in the second equation. The entire half at square term goes 0 because acceleration is 0 horizontally. So v equal to u. Horizontal initial and final velocities are same, but that we know because there is no acceleration. So this equation is not going to be anything useful. So I'm not writing that equation also. Even the last equation, v square equal to u square, you are not going to calculate anything from that equation. So even that equation becomes a useless equation. Means there is just one equation in the horizontal direction which is useful. So finding anything horizontal, like horizontal displacement, horizontal initial velocity, you have to use this particular equation. Now coming to the vertical direction. Here you can see acceleration exists. There is a vertical acceleration of 9.81. So none of these terms will get cancelled in the vertical direction. Means there are three useful equations in the vertical direction and there is just one equation which can be used in the horizontal direction. So using these four equations, three vertical and one horizontal, using these four equations we are going to solve all projectile questions. Consider one simple question. An arrow is fired to a target. The details are given and it's always better to draw the path of the projectile if it's not given in the question. Now the question asks you to find the time taken. The time. Time has no horizontal or vertical directions. Time is a scalar. Means if you are asked to find time in any of the projectile questions, then you can use either vertical equation or horizontal equation because time has no vertical and horizontal. I'm going to write SUVAT, but remember in the last topic we wrote SUVAT just once because it was all in one direction, but now you need to write SUVA twice because for horizontal direction and for vertical direction, but time is just one because it's a scalar. To find the time, I can use either horizontal or vertical depending on what is given. This is called the horizontal displacement, which is 15 meters. It's already given in the question. Now the vertical displacement, this is the vertical displacement, but the value is not given. So I'm just keeping it blank. Initial horizontal velocity, it is this. It's given, it's 36. Now the vertical initial velocity, you have to read it like the vertical initial velocity. You are firing perfectly horizontal and that's the initial velocity. What is the vertical part of it? We have already seen in the vector topic that no vector can have a component 90 degree to it. Means a horizontal velocity will have no effect in the vertical direction. Means the vertical initial velocity is 0. The final horizontal velocity, it's exactly same as the initial horizontal because you know there is no acceleration to change it. There's no force to change it. Final vertical velocity, that's a velocity on hitting this target here. This vertical velocity, I have no idea. So I'm just keeping it blank. Now the acceleration, we know the acceleration is vertically downwards. It's perfectly vertical direction. We want horizontal acceleration. What is the acceleration in this direction? We have already seen this before and we know it's 0. The horizontal acceleration is 0. The vertical acceleration, you should know it's 9.81. I am taking downward as positive because every quantity here is downward. So I am taking downward direction as positive. So I have written plus 9.81 and I am finding the time. I have written all the horizontal quantities, all the vertical quantities, and I want to find the time. I could use horizontal or vertical equation. I am going to decide what to use. Horizontally, I know many quantities. Except time, I know everything. But vertically, I don't know displacement, I don't know final velocity. So I have decided to use this equation, but horizontally. Everything what you substitute should be a horizontal quantity. Horizontal displacement is 15. Horizontal initial velocity is 36 and time I don't know. And horizontal acceleration we have already seen it's 0. So the entire quantity will go rearrange, make t as a subject and you got the answer. So this is how you do the projectile questions. Write so what, but sometimes you may have to write horizontal as well as vertical directions. Then choose the appropriate equation in the appropriate direction. All the equations should be written either horizontally or vertically. It's better to practice putting the direction on the top of the equation. Now let's use the same question to calculate another quantity. So the same question again repeated, but this time you are asked to calculate something different. Given that the height from which the arrow is fired is 1.5 meter, and you have to find the height from the ground where it will hit the targets. Like this d you are going to calculate, and I am going to write the quantities already what we have calculated before and whatever I know, but this time I am writing only vertical quantities because I want to find something vertical. If you want to find something vertical, no point of using a horizontal equation. I'm not writing horizontal quantities, all vertical quantities, and vertical displacement, actually I don't know. The total height I know, but that's not the vertical displacement of the projectile. It's coming and hitting at this point, not on the ground. So whatever I have marked in this white colored vector, that's actually the vertical displacement I don't know. Vertical initial velocity, that I know, it's 0. We have already discussed about this in the previous part. Final velocity, still don't know. This vertical final velocity I have no idea. Acceleration is plus 9.81. Time, of course we found the time in the previous step. These are the quantities in the vertical direction. Now my idea is to find the vertical displacement s, so that when you subtract it from 1.5 meter, you will get this distance d. So I want to find the vertical displacement. Which equation I'm going to use? You have 3 equations in the vertical direction. In the 3 equations, you have 2 equations which contains displacement s. The first one is ut plus half at square. I am going to use this because I don't know the final velocity. That's why I am not using v square equal to u square plus 2a. I have chosen the correct equation. Now I have to use the direction. As you know, we have to use this equation vertically because we are going to find something vertical. Vertical displacement is what we are going to find. Vertical initially 0, so the entire term will go 0. Acceleration is 9.81 into t square. Just rearrange and you will get 0.87 meter. Now how do you find d? Just subtract from 1.5. So 0.63 meter is the answer. Now let's find same question but a third quantity, that is the final velocity. Means this final velocity you are asked to find. What's the problem in using any equations of motion directly? The final velocity is neither vertical nor horizontal. Means you cannot use any horizontal equation or any vertical equation to find this. So what are we going to do? We have only one option. If you find any quantity which is neither horizontal nor vertical, the only option we have is split. Imagine the final velocity to be made of 2 components, a horizontal final velocity and a vertical final velocity. Obviously we can calculate the horizontal and vertical part because we have equations for that. What we are going to do is find separately the horizontal velocity and vertical velocity and then find the resultant. When you get the components, you know how to find the resultant using Pythagoras. I'm going to write all the horizontal quantities, all the vertical quantities from the previous part. Already we have calculated all these values. Both velocities I don't know. Let's say acceleration horizontally is 0, vertically is 9.81 and time already calculated. Now let's find the horizontal velocity first. Horizontal final velocity. Actually you don't need any equation for this horizontal velocity because you know the horizontal acceleration is 0, so no point of this calculation. Directly you can write horizontal velocity as 36. We have seen in the previous part the horizontal initial and final velocity will be exactly same because there is no force, there is no acceleration to change that velocity. But vertically it's different. I am going to use the same equation but this time vertically. I want to find the vertical final velocity, this yellow part. Horizontal part is already found. Initial velocity is 0. Acceleration is plus 9.81 into t. So you get 4.12. Now we got the horizontal part of it, the vertical part of it. Now we just need to find the resultant, and you know how to find the resultant. It's the Pythagoras. So this is the final velocity, the actual velocity of the body on hitting the target. Since the final velocity is a vector, Sometimes you will be asked to find the direction also. The direction means the angle. So let's see how to calculate this angle. You can imagine a triangle by moving the vertical component to the other side. Tan theta is opposite divided by adjacent, or theta is equal to tan inverse opposite side divided by adjacent side. Opposite side is the vertical velocity, adjacent side is the horizontal velocity. This is the direction of the final velocity with the horizontal. You can even find with the vertical also. Now let's move on to another important type of projectile, something thrown at an angle and it's coming back to the same height. Like this is the path of the projectile. The first quantity we are going to see is acceleration. As you know, acceleration is always vertically downwards for any type of projectile motion because the earth is always pulling it downwards. So the next quantity we are going to see is velocity. This is the direction of initial velocity. You are throwing something at an angle. Let's see what happens to the velocity as it moves upward. You can see the value of velocity is decreasing and the direction, it's becoming more and more horizontal because the earth is pulling it downwards. Both these changes are happening because of the earth pulling it downwards. So at the maximum height you can see the velocity becomes perfectly horizontal. There is no vertical part of it. It's just horizontal. Thereafter what happens? Again the velocity increases and the direction also becoming more and more vertical. All this because of the earth pulling it downwards. Here the speciality is the initial velocity and the final velocity are going to be exactly equal because it's a perfectly symmetrical path. The point where it starts, the same height it's going and hitting. So the initial velocity and the final velocity of this type of projectile will be always same. This type means the symmetrical path. If you throw something with 10 meter per second, it will come and hit exactly at 10 meter per second but in a different direction. This is the speciality of this type of projectile motion. Now let's see what will happen to the angles. Now let's see what will happen to each component of velocity, like the horizontal part and the vertical part. You will know by like the horizontal part. Now let's see what will happen to each component of velocity. The horizontal component u cos theta. You can see this is the component which is touching the angle. That's why it's named as cos theta. And this component is far away from the angle. It's not touching the angle. So we name it as u sin theta. We have already discussed this in vector topics. Okay, let's see what will happen to u cos theta and u sin theta during the motion. So let me consider u sin theta first. You can see what happens to the vertical part. All these changes are happening because the Earth's gravitational force directly affect the vertical part. It will go on decreasing at the beginning. It will become 0 at the maximum height. Again it will increase on the other side and it will collide the ground with exactly same velocity as the initial vertical velocity. Means the vertical velocity of the ball will go on decreasing and it becomes 0 at the maximum height. Again it will increase on the other side and it will hit the ground with a high vertical velocity. This is what happening to the vertical velocity. Once again you can see it will decrease to 0 at the maximum height. Again it will increase. Let's see what happens to the vertical component of velocity, that is u sin theta, during the motion. The vertical component will go on decreasing and it will become 0 at the maximum height. Again it will increase on the other direction and it will hit the ground with a high velocity. This is what happening to the u sin theta. Once again you can see it's decreasing and becoming 0 at the maximum height. Again it's increasing on the other side, and when it hits the ground it will have exactly same velocity as the initial velocity but with a negative sign because the direction is exactly opposite of initial vertical velocity. This is true only if the path is symmetrical, means the starting point and the ending point should be exactly the same height. Then only you will have initial vertical velocity exactly same as the final vertical velocity. Now let's see what happens to the horizontal component u cos theta. As we have seen in the previous cases also, nothing will happen to the horizontal component of velocity because there's no force acting in the horizontal direction, there's no acceleration happening in the horizontal direction. So at any point, any moment you take, it will be exactly same as u cos theta. Even at the time when it hits the ground, still it will be u cos theta. The values of vertical and horizontal, or even the resultant velocity, will be exactly same at the beginning and at the end. Only difference is the vertical velocity. If you have taken a positive value initially, finally you should take a negative value, but the value will be exactly same. As we have seen before, there are two types of displacements for a body in projectile: a vertical displacement and a horizontal displacement. You can see as the body moves to the other side, the horizontal displacement is go on increasing, and that horizontal displacement we call the range of the projectile. Now, what happens to the vertical displacement? Now, the vertical displacement will go on increasing as the body goes up, and it becomes maximum at the maximum height. And again, it will decrease and become zero. So, the vertical displacement of the body at the end of the journey is zero because it goes up and comes down exactly the same distance. So the final vertical displacement of this type of projectile is zero. So let's conclude the properties of this type of projectile. Like any projectile, this also has a horizontal and a vertical motion, and like any projectile, no force is acting in the horizontal direction, but there's weight acting in vertical direction. So there's an acceleration in the vertical direction, but no acceleration horizontally. So the horizontal velocity doesn't change. But vertical velocity, as you have seen, it will initially decrease, become zero at the maximum height. Again, it will increase on the other side. The horizontal displacement was increasing throughout, but the vertical displacement increased, became maximum, then decreased to zero. So the final vertical displacement of such a projectile is always zero. Now we are going to do a simple question in this type of projectile, and you can see it's a 5 marks question. So when you see 5 marks question, you have to realize one single equation cannot solve the problem. You may need to use more than one equation if the mark is more than 2 marks. Since you are asked to find something horizontal, then I am writing all horizontal quantities only. I am not writing any vertical quantity because I want to find something horizontal. So here, horizontal distance, I'm going to find horizontal initial velocity. This is the horizontal initial velocity, not u. I have to take only this much part because I need to write the equation only horizontally. So it's u cos theta, vertical initial velocity is u sin theta. Means in the equation you should be using u cos theta, not u. This original velocity will never come in any of the equation because it should be always either horizontal or vertical velocities. The final velocity, the horizontal and vertical velocity is going to be exactly same we have seen. So the final horizontal velocity is going to be exactly same as initial. Then acceleration, as you know, horizontally there's no acceleration. And time, we don't know. So let's start from the question. You are asked to find a horizontal distance. I am writing an equation horizontally because this is the only equation you can write horizontally. But remember, the acceleration horizontally is zero. We have already written that it's zero. So the equation becomes just ut. But remember, horizontal u is u cos theta. But now there's a problem. We don't know time. So I'm going to find the time. Already we have used one equation horizontally. So you have 3 more equations remaining, but all 3 equations in the vertical direction. So I'm going to use one of the equations in the vertical direction to calculate the time. For that, I'm going to write down all the vertical quantities. The vertical displacement, as we have seen before, the final vertical displacement is 0. Initial vertical velocity, as you can see there, it's u sin theta. Final vertical velocity, it's exactly equal and opposite to initial. So you can see the initial is plus 32 sine 40 and the final is minus 32 sine 40 because they are exactly opposite to each other. Now the vertical acceleration. Since I have taken the upward velocity as positive and downward velocity as negative, I have to take the acceleration as minus 9.81 because acceleration is downward. So the downward final velocity I have taken negative, so the downward acceleration also I should take negative. I know every quantity here, so you can use any equation of motion. You have two options. So I'm going to show you how to use each of the equation. You need to use only one, but I am going to show both equations. The first one is ut plus half at square. Remember, we have already used this horizontally, so now we are going to use this vertically. Put everything vertical. The vertical displacement is 0. Initial vertical velocity is 32 sine 40 into time plus half into minus 9.81. Be very careful. You have to substitute the correct sign. I'm going to bring the minus things to the other side so that it will become positive. So you will get like this. You can cancel one t from both sides and you rearrange and make t as the subject. You get the answer. Now I'm going to show you how to use the other equation, that is v equal to u plus at. Again, the quantities are same. I'm going to use v equal to u plus at in the vertical direction, everything vertical. The vertical final velocity is minus 32 if you have taken initial as plus 32, and acceleration it's minus 9.81. So I'm going to bring all the negative things to the other side. Every negative will become positive. 32 sine 40 plus 32 sine 40, because this one I'm bringing this side so that it will become positive. Now you can make t as a subject and you get the same answer. I'm going back where we were stuck without getting the time. So now we have got the time value, that is 4.2. So directly substitute the time and you got the horizontal distance. Let's move on to a more realistic question. This is a type of fish who spit on its prey to catch it. So what you can see is the path of the spit, which is a projectile path. And the question says the spit is going at a speed of 3.5 at an angle 70 degree to the horizontal. It travels a horizontal distance of 0.4 meter. What height is the insect? Means you are going to calculate the height of the projectile. From the question, it's clear that you are going to find a vertical quantity. So I'm not going to write anything horizontal. I'm writing all vertical quantities. Vertical displacement, I'm going to find vertical initial velocity. You can split the initial velocity into two parts, and the vertical part will be 3.5 sine 70. Again, you know why it's sine 70. It's a component which is not touching the angle. That's why it's sine component. And vertical final velocity, we can't write minus 3.5 sine 70 like before, because this is not a symmetrical path. So we have no clue about the final position. We don't know even if it's maximum height or not. So I'm just keeping it blank. Acceleration. The initial upward velocity, you have taken a positive value, you have written it as positive. So the acceleration, you have to write it as negative, because the upward value you have taken positive. So the downward acceleration, you have to take negative. The time is not given. I want to find the vertical displacement. So I'm going to write an equation for vertical displacement. Every quantity should be vertical, as you know. Vertical displacement, I don't know. Vertical initial velocity is 3.5 sine 70 plus the acceleration should be written as minus into t square. Now the problem is we don't know t. So now the problem is we don't know t. So there's no way to get displacement without knowing the time. I'm using the horizontal direction. I'm going to write all the horizontal quantities because I want to find the time. For vertical direction, I couldn't find the time. So I'm going to find time using a horizontal equation. I'm writing all horizontal quantities. Horizontal distance is given. Horizontal initial velocity is the cos component. Horizontal final velocity will be exactly same, because there's no acceleration horizontally, and horizontal acceleration is 0. I'm going to write the only possible equation in the horizontal direction, that is s equal to ut. And acceleration is 0, as you know. So I'm substituting everything. I can get the time from the horizontal direction. Then I'm going to substitute the time to the vertical equation here and here, t square. So you will get the answer for the vertical displacement, or the height where the insect is situated. In all the questions whatever we discussed, it was directly given which quantity is to be found. But there will be sometimes questions like you have to decide which quantity to be calculated first. For example, in this question, the goalpost is 11 meter away and you are kicking the football at an angle of 15 degree at a speed of 26 meter per second, and it's going to a projectile motion. The height of the goalpost is 2.4 meter. The question is, will the goal be scored or not? If you want to know whether the goal is scored or not, what you want to find is what will be the vertical height of the ball. What will be the height of the ball when it has traveled 11 meter distance? By the end of the 11 meter, what is the vertical position of the ball? That will decide whether it will go into the goalpost or it will go above the goalpost. So what I'm going to find is what is the vertical height when the horizontal distance is 11 meter. But there is no direct equation connecting horizontal distance and a vertical height. There is only one quantity which can link between horizontal and vertical things, that is the time. Time has no vertical or horizontal, so that's the only link between the horizontal and vertical motion. What I'm going to find is the time taken to travel 11 meter, and in that time where is the ball vertically. 11 meter it travels horizontally, so vertical height I'm going to find. Initial horizontal is the cos component and initial vertical is the sine component of the velocity. Final horizontal will be exactly same as initial, but final vertical I don't know because it is not a symmetrical path, so I can't take the negative value or anything. Acceleration, horizontally it's 0 and vertically it's minus. Because the initial upward velocity I have taken positive, I have to take downward acceleration as negative. And the time I am going to calculate now. And the only equation in the horizontal direction is s equal to ut. And acceleration is 0. Now I'm going to find what will be the vertical height of the body at the end of 0.44 seconds. I'm going to write a vertical equation because I want to find the vertical height. Vertical velocity is 26 sine 15. Time already we have found it's 0.44. Again, the acceleration you have to take negative because the upward velocity you have taken positive, the downward acceleration you have to take negative, and the displacement you get is 2.01. But the question says the height of the goalpost is 2.4. So at the end of 0.44 seconds, the ball is clearly below the bar. So it will certainly be going into the goalpost and he will be able to score a goal like this. Now moving on to the last calculation. This is a person doing a long jump and you can see what change he is making in his position during the jump. You can see when he is landing, he is sitting down. He is taking off from a standing position, but he is landing in a sitting position. So what is the advantage of sitting down when you land during a long jump? The advantage is you are moving your center of mass vertically downwards. So when you lower your center of mass, there is a vertical motion. But at the same time, there is a horizontal motion also. The advantage is you can cover longer distance. So we are going to do a calculation based on that. The question says, because he is sitting down, he is able to lower his center of mass by 50 centimeter. As a result of this vertical motion 50 centimeter downwards, how much extra horizontal distance he can get. So this is a simplified picture of that. The initial velocities are given, vertical and horizontal velocities are already given. The vertical displacement is also given. What you are going to find is the horizontal distance traveled. The extra horizontal distance means this yellow colored line. I am considering the motion only inside the circle, because it's not asked to find the total distance, only the extra horizontal distance. So let's see what details do you know about the motion inside the circled part. The horizontal velocity remains same throughout the motion. So it's going to be the same at the beginning of the motion circled. The vertical velocity also will be exactly equal at that point because it's the end of the symmetrical path. So we know the initial horizontal and vertical velocities of that point, and we know the vertical height. Since I am finding something horizontal, I am going to write all horizontal quantities and time. Horizontal distance I am going to find. The horizontal initial velocity of the path is 8. And final, obviously it will be same because there is no acceleration in horizontal direction and acceleration is 0. So let's write an equation in the horizontal direction, and this is the only equation possible to write in the horizontal direction. Now I want to find the horizontal distance, but I don't know the time. So first I'm going to find the time. For that I have to use a vertical equation because the only horizontal equation is already used. So I'm going to use a vertical equation now. For that I'm going to write all vertical quantities, SUVA. Vertical displacement is given, it's 0.5, it's given 50 centimeter, so it's 0.5 meters. Vertical initial velocity is 2.8. You can take 2.8 or minus 2.8, but I am taking downward as positive because every quantity here is downward, so it's easy. The vertical final velocity, I don't know. And the vertical acceleration, the downward acceleration is plus 9.81. So if you have taken the initial velocity as plus 2.8, the acceleration also you can take plus 9.81. Using these vertical quantities, I am going to calculate the time. So the equation what I can directly use is ut plus half at square, but everything should be vertical. I am substituting all the values, but the problem here is there is a t and a t square. So you need to use quadratic equation. So you can use the calculator to substitute the equation and you can get the time as 0.14 seconds. This is one method. But if you don't want to use the quadratic equation, then you need to use two equations. If you use quadratic, just one equation, you can get the answer. First, I am using this equation in the vertical direction and I don't know the final vertical velocity and initially is 2.8. So like this, I can get an equation, but still the problem is the vertical final velocity I don't know. So I am going to use again another equation to find. So now you can substitute the time here, then you got the horizontal extra distance, that is 1.12 meters. Next, we are going to see how each factors will affect the motion of a projectile. So let's take one by one. First is initial velocity. For example, an object is thrown with an initial velocity u and it follows this particular path. It's traveling a horizontal distance s. Now I'm going to increase the horizontal initial velocity. This velocity is increased. How this change will affect the projectile motion means how it will affect the range, that means the horizontal distance, and the time of flight and the final velocity. How these three quantities will be affected by the increase in initial horizontal velocity. If you want to explain the changes, you need to use corresponding equations. For example, the equation for range is s equal to ut. You know, this is the only equation which you can use in horizontal direction. Now the u has increased, but what happens to the time? So we are not sure about whether the time has increased or decreased. Without knowing about the time, you cannot comment about the range. So I'm going to find what happens to the time first. I'm using this equation, and you know why ut is missing, because initial vertical velocity is 0 since it's thrown perfectly horizontal. The height of the projectile doesn't change. I have changed just the initial velocity, I have increased. Nothing happened to the height of the projectile, so h remains the same. And acceleration. Acceleration is always 9.81. Whether you throw with a small velocity or a big velocity, the acceleration is going to be same throughout. That means h and a are constants, so the time also should be exactly same. Means if you throw at a small velocity or a big velocity, the time taken to reach the ground will be exactly same if you throw from the same height. So the time of flight depends only on the height of the projectile, not how fast you are throwing it horizontally. So now we have learned the time is constant. As a result, when the initial velocity increases, the range should increase. So the new path with the increased velocity will be like this. It will travel more horizontal distance. Now, the final velocity. As you know, the final velocity is always a combination of vertical and horizontal components. So we are going to see what happens to each of these components. For example, the vertical component. Nothing will happen to the vertical component since there is no change happening in the vertical direction. The only change is horizontal velocity has increased. So the horizontal component should increase because the initial horizontal velocity is increased, and the horizontal velocity, as you know, it will remain same throughout. So the horizontal velocity will increase and the vertical doesn't change. As a result, the final velocity will also increase because it's a resultant of horizontal and vertical components, and the horizontal part has increased. The resultant velocity will increase. Now the next change is height of the projectile. For example, I am throwing something from a particular height at a particular speed, and it's falling there at a distance s away from the point of projection. I'm going to throw it with the same speed from a different height. I am increasing the height of the projectile, but I'm throwing with the same speed. What will happen to the range, the time of flight, and the final velocity? That's what we are going to see. So let's see one by one the range. As you know, this is the only equation to find the range. The initial velocity doesn't change, but I want to know what happens to the time to know what happens to the distance. In order to find the time, I'm using the vertical equation. This time the height has increased. The acceleration is a constant, but the height has increased. So the time should increase. Since the height is increasing, the time should increase. So it will take a greater time to reach the ground if you throw from a greater height. Now we have seen the time increases and the initial velocity remain the same. So the horizontal range, the distance, should increase. The projectile will be following this path. It will move a greater range, but it will take more time. Let's see what happened to the final velocity. As you know, it's a combination of horizontal and vertical parts. Here, the horizontal part, nothing will happen as there's no change in the horizontal velocity from the beginning. But since the height has increased, it's traveling more distance, so the velocity will be also more since it's accelerating. So what you see is the horizontal velocity is constant, but vertical part has increased. Means the resultant also should be increased because it's a combination of both. So the final velocity will increase if you throw from a greater height. Now we are going to see in the other type of projectile, the symmetrical projectile, what will happen if you increase the initial velocity. Let's say you are throwing something with a velocity u, it's traveling a distance, and the maximum height of the projectile is h. I am going to increase the initial velocity. What changes you can observe in the range and the time taken? As you know, every equation should contain either u cos theta or u sin theta because all equations we have are either horizontal equations or vertical equations. In order to know the range, I am using s equal to ut, but remember u means u cos theta here. That's the horizontal velocity. U cos theta is increased because u is increased, but I have no idea about the time. Will it take more time or less time to reach the ground? So in order to know the time, I am using a vertical equation. This equation is actually v equal to u plus at, but you know the final velocity will be exactly opposite to initial velocity. So initially if you take u sin theta, finally you can take minus u sin theta. That's why I directly wrote like that. Now when you rearrange, u sine theta you can bring to the other side, it will become 2u sine theta. At you can bring to the left hand side, and the acceleration is negative. So we have done this before, so I'm directly writing the equation t is equal to u sine theta over g. U has increased and g remains the same. Since u has increased, the time also will increase. So it will take more time to reach the ground if you throw with a greater initial speed. Now we have seen the time increases. So since the time increases, the distance also should increase, because already u cos theta is also increasing. So the range should increase. You can see the path followed by the projectile. It will travel more horizontal distance, and the maximum height also will increase. Next quantity we are going to check is what will happen if the angle of projection has increased. So I'm projecting with some angle and this is the path followed. Now I'm going to increase the angle. So we are going to see what will happen to the range and what will happen to the time taken. As always, it's a combination of horizontal and vertical parts, and directly you can see as always it's a combination of horizontal and vertical components. As the theta increases, what will happen to sine theta? As the theta increases, the sine theta value also should increase, because sine 0 is 0 and sine 90 is 1. What will happen to u cos theta as the theta increases? Cos theta will do the reverse, because cos 90 is 0 and cos 0 is 1. So it's exactly opposite to sine theta. U cos theta has decreased, but still I'm not sure about the time, so I'm going to find out what happens to the time. For that I'm using the vertical equation v equal to u plus at. Directly I'm writing because we have done this before. What happens is u sine theta has increased, so the time will also increase. Coming back to the first equation, the time has increased but u cos theta has decreased. What will be the result? So what actually happens is, up to 45 degree, as you increase the angle, the range will increase up to 45 degree. At 45 degree, you will get the maximum range. So the maximum range of a projectile will happen exactly at 45 degree. Now above 45 degree, if you increase the angle, let's say I'm making it 60 degree, you can see the path of the projectile, the range of the projectile will decrease. So up to 45, the range will go on increasing, and above 45, the range will begin to decrease. So this is the effect of increasing angle in these type of projectiles. Now we are going to the next quantity. I'm throwing something with an initial velocity and angle theta, and this is the path followed by the projectile. And this is the horizontal range. Now imagine you are throwing the same thing with the same angle and the same speed, but on the surface of moon. So how the path will change? What will happen to the range? And what will happen to the time taken? The only difference between Earth and Moon is the acceleration. The acceleration on the Moon surface is less than that of the Earth. So let's see how this difference affects the motion. I'm going to find what happens to the range first, and this is the only equation. U doesn't change, theta doesn't change. I'm not sure about the time. So let's find out what happened to the time. I'm directly writing the equation. The g value is decreasing. On the moon surface, the value of g is less than that of the earth. As a result, the time taken will increase because they are inverse. Since the time has increased, the horizontal range also should increase. Means this will be the path followed by the projectile if it is thrown on the surface of moon. The next factor is air resistance. You can see the two paths followed by a projectile. One path is without air resistance, the red colored one, and the green colored one is with air resistance. How you are going to explain the difference? This question was for 6 marks, means you need to write 6 points. Air resistance will always oppose the motion. Motion means velocity. It will oppose both vertical and horizontal velocities. So we are going to see separately what influence air resistance has on vertical motion and also horizontal motion. In case of vertical motion, what happens is it will exert a force downwards. So the air resistance will be pushing it downwards. Now there are actually two forces acting downwards, weight is already downwards. So what happens is the downward acceleration will now increase. It will be more than 9.81. So with air resistance, the height will decrease because there are two forces pushing it downwards. Now let's see what air resistance does to the horizontal motion. Usually in horizontal motion, there is no acceleration, but this air resistance will exert a force against the horizontal velocity. As a result, there is a deceleration horizontally. The velocity has decreased, and as a result, the distance traveled will be less. Now, two more factors we will see very quickly. One is the mass of the projectile. Mass of the projectile has nothing to do with any quantity in projectile motion because you don't see any term mass in any of the equations we use. The time taken, the range, the height, nothing will change if you change the mass. Again, this also has no effect on the projectile motion because you don't see a term radius or diameter in any of the equations we used. So with air resistance, the conditions are different. If heavier, then air resistance will have generally less effect on the mass. But if it's a very big body, then air resistance will have a bigger effect on the body. Now let's move on to the last part, that's a graph. How do you represent the projectile motions on a graph? Let's consider this simple type of motion. What you have already learned is it's a combination of a horizontal and a vertical motion. And the horizontal and vertical motions are completely independent. Means you will need two graphs to represent any projectile motion. One graph you will need for horizontal quantities, one for vertical quantities. You cannot draw horizontal and vertical quantities on the same graph. So let's see how can you do separately. I'm drawing horizontal quantities first. Horizontal acceleration. As you know, there is no acceleration horizontally. So I have drawn a line at 0, but not needed. Horizontal velocity. As you can see, horizontal velocity remains constant because there's no force in the horizontal direction. There's no acceleration in the horizontal direction, so velocity doesn't change. Horizontal displacement. The horizontal displacement should be like this because the gradient of this graph should give the velocity, which is a constant. So you need a graph with a constant gradient. There is an acceleration and the acceleration is constant. I'm taking downward as positive, that's why you get a positive value. You are going to plot a graph here whose gradient is acceleration and which is a constant positive value. So the shape of velocity graph should be like this because it should give a constant gradient, which is acceleration. Now I'm going to plot the displacement time graph. The gradient of this graph should give the velocity. Means the gradient should be initially 0 and the gradient should then increase to maximum and the gradient should be all positive. So this is the shape of displacement time graph. The gradient should be initially 0. How do you find the gradient of a curve? By plotting tangent. You can imagine a tangent here. It's a horizontal line. A horizontal line has 0 gradient. Means the initial velocity is 0. Then when you draw the tangent, it's increasing. It's going to a vertical line. Means the final velocity is higher velocity. Then you can see at any time, any point if you take, the gradient is positive. Now let's see the other type of projectile motion, which is the symmetrical path. And we need separate graphs for vertical and horizontal motion. In any projectile motion, horizontal acceleration is 0. The reason you know there's no force horizontally means the horizontal velocity should remain constant and the displacement should be increasing uniformly. In the vertical direction, there is an acceleration. This time I'm taking downward as negative because there are two directions involved throughout the motion, whether it's going up or coming down. The earth is pulling down and the acceleration is minus 9.81. You are going to plot a graph here whose gradient should give the acceleration. Means the gradient of the graph you are going to plot here should be a constant, should be a negative value. So I'm going to plot a graph whose gradient is a constant and negative. Gradient of the graph should be velocity. The gradient should be a high positive value at the beginning. Gradient should be decreasing to 0. Then the gradient should increase on the negative side. First half should be positive gradient. Second half should be negative gradient. And this is the shape. You can see initially when you draw the tangent, you get a high value because it's almost vertical. So the velocity is high. At the middle, when you draw the tangent, it's horizontal line. means the velocity becomes 0. Horizontal line has a 0 gradient. Then again the gradient increases, but this time it's all negative. You can see this side will have all negative gradients. With this, we will conclude the discussion about projectile motion. Thank you.